something we need to check first just to make sure. We want to try the integral test, considering this is central to what we're doing. Yeah, it has to be continuous, decreasing, and what else? What's the last thing? To 0, exactly. That's just cursory, because if it's not continuous, you run into big problems. If it's not decreasing, it's definitely not going to converge. If it doesn't go to 0, it's not going to converge. You can just
decreasing and just say it's continuous and it goes to 0?
Sure. By implication, sure. But I mean, it's continuous decreasing and going to 0. So we're going to try this integral. What integral are we trying to evaluate here? The limit as n goes to integral of 1 to n of x squared plus 4 dx, like this. The challenge is that's almost in the form you want. It's almost in the form you want. Let's just do you want to rewrite it a little bit? Can we rewrite this a little bit? What is it almost like? It almost looks like what? It almost looks like the integral of x squared. We want it to be x squared plus 1, right? How do we turn that into x squared plus? What do we do in order to turn that? What? You want to do u equals 2x? Sure. Okay, so if you did u equals 2x, that's fine. Du is equal to 2 dx. Okay, sure. So dx is du over 2. Okay, so hold on, let's just see what happens. Let's just see what happens. So you're saying if we do this, what happens? If we make this substitution?
You get
1 over x squared plus...
No, 4u squared.
I haven't made the substitution yet. I'm only doing the dx first, okay? So we have du over 2. I'm just going to do this in pieces. But now, one thing, we set u is equal to 2x. So what does x equal? U over 2. So if you take this, and I'm kind of doing a operation for multiple steps at once. You end up with u over 2 what? Squared plus 4 times du over what? 2. And you have this integral, right? Do we have to? Oh, I don't know why it does that there. Sorry, guys. What do we need to? Are we okay so far? We're heading towards what we want. We're heading towards what we want because we now have 1 over u squared over 4 plus 4 times du over 2. We haven't written in the rest, though. What else do we need to write in here? Do we need to change the limits of integration? What are the limits of integration going to become? From what to what now? They were x values, and now they're u values, so it goes from 2 to what? 2n. That doesn't really change much, right? It's still going...
We might as well call 2n.
Well, let's just keep it there for consistency's purpose. So it's the limit as n goes to infinity. So I'm writing the whole thing. Now, why is this helpful? It looks like a mess, but what can we now kind of factor out of the bottom? What?
Not a 4. We did it wrong.
Did we do it wrong?
Yeah,
It's close. Hold on. I understand here. But it's close to what we want, right? We want to be able to do something to this to turn it into something squared plus 1. So if we want to do that, we need to pull a 4 out of the 4 to make it a 1. So we need to pull a 4. Oh, we need to glue a 4 on there. Were we really close?
Yeah, we should have made it 2.
Okay. So I'm not going to erase this, but I'm going to say this is all correct. Like, there's nothing wrong about this, but it's close. It's not what we want, okay? So try 2. Let's try this out. Try 2, and just leave it like that so we can always go back to see if we need to modify something or learn. Let's instead say, what do we want to say? U is equal to, how about just 1/2 x, right? Just du is equal to 1/2 dx, right? So now when we make the substitution, we end up with u is so it's 1/2 to n over what? N over 2. And instead it's going to be 1 over 2u squared plus 4. And what does du equal? 1/2. Excuse me. 2 du. Sorry, dx is equal to 2 du. And this is the limit as n goes to? I totally understand. It's me trying to write too many things at once. Are we okay right now? What's kind of cool about this is, what can you now factor out? I'm going to write this all out so we have all the pieces. We're going from 1/2 to n over 2 of 1 over 4 times u squared plus 1 times what? 2 du. That's really helpful because what does that equal? The limit as n goes to infinity of the, what can we factor out to the front of this integral? Actually, the front of the limit, really. 1/2, right. So let's just take that whole thing out so we don't have to deal with it. The 1/2, and we're going from 1/2 to n over 2 of what? 1 over u squared plus 1 du. Now, is that something we can integrate now? Yay! It's something we can integrate. Yay. It's the u squared plus 1. So now we have 1/2 of the limit as n goes to infinity of, what is it? Tan inverse, yep. Of what? Of u, and we're going from to n over 2. We have to be real careful here about this. Let's just be as careful as we can because we want an exact answer, or we'd like to get something nice. I understand you can fudge a little bit here because all we're trying to show that this goes to,
All we have to show is that this is
it's bound, it goes to a constant, right? It doesn't go to infinity, right? That's what we're looking for here, but let's just be careful, okay? So if we actually do this now, we end up with 1/2 times the limit as n goes to infinity of tan inverse of n over 2 minus tan inverse of 1/2. Right, exactly. So what does this go to right here? Pi over 2, right? It's the sideways s, right? And then do you know what the tan inverse of 1/2 is? You don't care, right? You just know that this now equals 1/2 times pi over 4 minus tan inverse of 1/2. Does tan inverse of, it is constant. This is constant, right? So what can you say about this series? It's convergent. And the reason you get to say that is this. There is something, I want to be really clear about this. There's this monotonic series theorem. What did it say here? I always get it mixed up. Every bounded monotonic sequence is convergent. So we just proved that this monotonic sequence is bounded, so therefore it has to be convergent. Yes? So first of all, it is continuous. We like that because you're only looking at, remember, 3 to infinity on this thing, right? Let's do this right there. Great. So is it decreasing? How do you know it? How do you know if this thing is, first of all, let's write this in the right parentheses. It's 1 over n times ln of n times ln of ln of n. That's really obnoxious is what it is, especially without the parentheses. Well, first of all, let's just analyze this for a sec. That's going to go to infinity, right? This is going to go to infinity. This right here is going to go to, so therefore this right here is going to go to, so therefore this thing is going to go to. Nice. Okay. We followed the chain. That's all I want right there. That's great. Does that make sense, everybody? So it's getting big on the bottom very quickly, and it's staying constant on the top, so it's going to 0. So it's decreasing. Yay, it's all positive, right? It's all positive. So we have what we want. It's continuous, positive, decreasing, going to 0. Nice. So now we need to see if we can do the integral. What integral are we trying to do? The integral from what to what?
from, what was it, 4 to infinity.
You want to do 4?
Well, 3 to infinity.
It really doesn't matter, right? Because
4 will be included in the 3 to infinity.
sure.
We just want to keep 3 out of it just in case.
Okay. Sure. Sure. So you want to do 4 to infinity like this? Of 1 over
1 over
x ln of x dx, and it's the limit as n goes to infinity. Change the, oh, it's not to infinity, it's to n. Okay, nice. Ready? Here's the magic one. This is just equal to, yeah, you're not going to get that. Limit as n goes to infinity, or at least not in the next like 10 minutes. Ready? ln of x. It does work. To n, right there. It does. It does work. It do, do you really care? I'm just going to take, is it okay if we take it on faith that it works? Well, yeah, we can derive it, but the only reason we have this to derive is because I just gave it to you in the first place. Yeah, so yeah, we could derive it. I don't want to focus on that because I want us to get to more BC topics. But the point is, if that's true, what happens to that? Ln of x in the middle goes to infinity, right? The ln of something getting big gets big. The ln of something getting big gets big. So this thing is going to go to what? Infinity, so it's divergent. This one's annoying because you know what? Going from here to here, I'm not sure about that. I mean, you have to use the chain rule twice, right? Not cool. Not cool. Not cool. Trying to integrate on 23. You're trying to integrate on 23. Read it to me.
1 over.
Well, 1 to infinity of.
2 to infinity.
Well, just do 1. Okay, you can do this. It's okay. X cubed plus x dx. That's what you're trying to integrate, right? Now, here's the thing. This is equal to the integral from 1 to infinity of 1 over x times x squared plus 1 dx. Now use partial fraction decomposition, and you can integrate this thing. Suppose that you have the sum of an and bn are series with positive terms. If bn is convergent and an is less than bn for all the n, then an has to be convergent. If bn is divergent and an is greater than bn for all n, then an has to be divergent. So basically what you get to do now is really fun, which is you get to remember what you know are convergent and divergent series and prove that each matched term is less than or greater than something that is divergent or convergent, and then you get a useful answer, right? So for this one right here, determine whether this series converges or diverges. If we want to prove it converges, we need to find a series that we know converges where every mapped term, correlated term, is greater than this one. So if we want to prove convergence, we need to find a series that we know converges that is greater than each of these terms right here. That is greater than each of these terms. Now, just to help things out here, I'll give you a hint. In terms of the n behavior here, what are the only terms that are really going to matter in terms of the size of these pieces? The n squared, right? The n squared. Oh, wait. Well, be better than that. You have to be careful. 5 over 2n squared. You got to just, you don't have to, but
You can kill the 2 because that's making it smaller.
no, I understand that, but let's just be overly complete to make it as easy to see as possible. Sometimes when you make it a little too general, it's hard to see the mapping. I totally understand what you're saying. Let's just go with this. You know, for example, that 5 over 2n squared plus 4n plus 3 has to be, and if remember n is going from 1 to infinity here, has to be less than 5 over what? 2n squared. Just stop there first. Is that correct?
Yes.
Why is that correct? Because the 4n plus 3 is positive and it's making the denominator bigger, correct? And what is this equal to? 5 over 2 times 1 over n squared. I just want to leave it like that. This is clearly true, right? Do you agree with that right there? So what do we now know? We know that the sum, because we just know this is true, the sum from 1 to infinity of 5 over 2 times 1 over n squared, like that, is equal to 5 over 2. This is kind of like limits when you had to show too much. 1 over n squared. We know something about that. What type of series is that? This is a p series, and in this case, p is greater than 1, so it converges. So therefore, this is convergent. Does that make sense? We just showed that every correlated piece is less than every other one, and therefore we know that this one has to converge. Okay, what about this one? This one looks fun. Does it converge or does it diverge? Converge or diverge. So we have to make it look like something that we know converges or diverges. Any ideas? No, you're right. So what do you know about this? You know that ln of n over n is greater than 1 over n, right? So this right here, n equals 1 to infinity of ln n over n. For n greater than what? This n greater than what? N greater than e, right? So it's okay that this goes up. It's a little bit less, but for the rest of it, it's above, right? For a finite span of time, it doesn't work. But the infinite darkness that is infinity, or
Basically, from e to infinity.
we don't care about the beginning. Remember, we can shave off the beginning. Okay, we're just doing some little hand waving math here. Correct. So we know that this right here is going to be greater than the sum of, to be n equals, how about, let's just say this, 3 to infinity is going to be greater than this from n equals 3 to infinity of 1 over n. And we know that this right here is divergent. So this is divergent. Does that make sense? Cool. Okay. Let's look at what this says. The limit comparison test. Suppose that an and bn are series with positive terms. If the limit as n goes to infinity of an over bn equals c, a constant, and c is greater than 0, either both series converge or both series diverge. Either one or the other, right? So how are we going to use this?
Isn't this basically that?
It kind of looks like maybe you could use this original comparison test right here just by comparing series, right? What does it look like you might be able to compare it to? it looks like you can compare it to 1 over 2 to the n, right? And what do you know that 1 over, that's a weird dyslexia. Yeah, it's weird. What do we know about this? Not to n, to infinity. And I just deleted that. What was this supposed to be? 2 to the n to infinity. What do we know that equals? What's 1/2 plus 1/4? No, 1/2 plus 1/4 plus 1/8 plus 1/16. You get halfway, halfway, halfway. It's convergent. What does it go to? It goes to 1. So this is convergent, right? However, 1 over 2 to the n minus 1 is greater than 1 over 2 to the n. What do we know about bigger than convergent? Equals, don't know. You don't know. Like, shut up. You don't know. Does that make sense? So you look at your comparison test and you say, okay, I can't really do much with this, right? So what we're going to do instead, we're trying to, so this right here is our first attempt, and we're like, oh, frowny face. Okay. So instead, we'll try to, I'll bring this down so we can get it out of the way. Try to. What did that limit comparison test say? It said that if you have the limit as n goes to infinity of an over b to the n, it goes to a constant, they're either both convergent or they're both divergent, right? So what we're going to look at here is we're going to try to say the limit as n goes to infinity of, let's say, let's put it up here. We want to pick something that we know is convergent, such that when we put it in the denominator, it turns the whole thing into something that is convergent. Does that make sense, everybody? So we want to put something that's convergent here, or something we know that is divergent, either one, right? Because if we show that it equals c and that thing is convergent, the numerator has to be convergent as it goes to infinity, right? Does that make sense, everybody? Or one or the other. We have to put a known divergent or convergent series down there. Anybody want to guess as to what we're going to put down there? We were really close before. 1 over what? How about 1 over 2 to the n? We want to get something that matches the behavior, right? At least in the important ways. Do you agree with that? You want to match the behavior at least in the important ways. So we know that that's convergent right there. So let's do the actual limit. The limit as n goes to infinity, what does this become? 2 to the n over 2 to the n minus 1. What can we apply? Can we apply L'Hopital's rule? We can, and you just answered the next question. You could use L'Hopital's rule, and what do you end up with? The limit as n goes to infinity of what? Yeah, ln 2 times 2 to the n over what? Yeah, what is that? 1. So therefore, oh wait, it does! And I'm not sure why that is going to come up there, and I'll just make that go away by doing that. It goes to 1. So what do we now know? By the limit comparison test, therefore, the limit as n goes to infinity of 1 over 2 to the n minus 1 must go to something. We don't know, so we know it is constant.
Therefore, it's
Convergent. Cool? Does that make sense?
Actually, it goes to
Go, shush, shush. Don't critique my handwriting. I'm excited, okay? I like this stuff. It's contour. That's what I need to do. I need to build in a totally made-up math word that sounds real that you're going to bring with you to college, you know? But the thing is, there's enough words that just sound crazy anyway. That's why it'd be too easy for me to do. Like, has anybody seen this? WLOG? Log? You never say it out loud. Anybody know what that stands for? I'll give you a big gold star if you know what that stands for. It's a big kid math phrase. Seen this before? If I said, what does this say? Ready? Ready? Oh, let me get an actual cursor. X greater than 2. Anybody know what that says? For all x greater than 2, there exists.
your E is a little bit weird.
Yeah. Well, it's not a yes. There exists a C contained in the real. There's a lot of ways to do this. Like, does anybody know if you? I think it's if you put an exclamation point before something. It's not. Well, that's in coding languages. Then unique. I forget. There's a lot of different ways, but there's what is it? Do you remember? Is it all comes down to choosing. So we're going to do the limit as n goes to infinity of 2n squared plus 3n all over the square root of 5 plus n to the fifth all over something. And we want to choose something so that it equals a constant. Anybody have an idea of what we should choose? Anybody have an idea of what we should choose? Again, focus on the things that really matter. What really matters in the numerator of the numerator of the numerator? 2n squared is the thing that really matters. What's the thing that really matters in the denominator? The square root. Oh, you go one more. Thank you. I can't quite keep up. You're very good. Look, it's the square root of n to the fifth, so n to the 5 halves. Exactly. Those are the things that dictate the real behavior. The 5 throws it off a little bit, and the 3n throws it off a little bit. But as n goes to ballistically large land, they become infinitesimally unimportant, right? So what are we going to, I'll do some different colors here. What are we going to put on the bottom? 2n squared over, let's just do this. For example, n to the, is that okay if I leave it like that for now? Now, look what happens. The limit as n goes to infinity, well, let's clean it up first. Is that okay? Let's clean it up first. So we have 2n squared plus 3n times n to the what? 5 halves, all over the square root of 5 plus n squared times 5n to the n to the fifth. Thank you. That's important. N to the fifth times 2n squared. Nice. Okay, well, hold on. The top definitely goes to infinity. The bottom goes to infinity. So what can we apply? We can apply L'Hopital's rule. So now we need to take the derivative. Now, here's the thing. We need to just be careful about this. What should we do before we do L'Hopital's rule? Can we clean it out? Can we clean it up a little bit? Is that okay? Well, okay, I'm going to say it is, okay? So it's going to be 2n to the 9 over 2, right? No? It's 2n squared times n to the 5 over 2.
Oh, yeah, that's right.
I can add fractions.
Yeah,
Plus 3n to the 7 over 2 all over, what is this? 5 plus n to the fifth to the 1/2. Put the 2 out front and make it n squared. Okay, biggie, yes. What you can do is you notice that you could actually take out, you could cross that n squared off right here. Let's just do that right here. That can go away. If we do that, what does that 9 become? It becomes a 5. And what does that 7 become? A 3. Thank you. So now we have, so biggie, is that okay? I understand we're effectively doing the exact same thing now, okay? We're effectively doing the exact same thing. So we have 2n to the 5 over 2 plus 3n to the 3 halves all over 2 times 5 plus n to the fifth to the... That was kind of helpful because it means we don't have to use the product rule on the bottom if we're going to use L'Hopital's rule. So you want to use L'Hopital's rule? What do you think? All right, so look, let's apply L'Hopital's rule right here. And what do we end up with? The limit as n goes to infinity of 5n to the 3 halves plus 9 over 2n to the 1/2. The 1/2 drops, cancels with the 2, right? And you end up with, oh, I forgot about something. Never mind. I was happy for the wrong reason. N to the fifth to the what? Times what? 5n to the fourth? Yeah. Because the 1/2 dropped to the front and canceled with it. Oh, we can move everything up. So now we have limit as n goes to infinity. Let me write it up first. So we end up with 5 plus n to the fifth to the 1/2, right? Times 5n to the 3 halves plus 9 over 2n to the all over 5n to the fourth. Ah, wait a minute. Let's just look at that for a second. Is there anything definitive that we can say about that? I kind of maybe sort of want to say the bottom is growing larger than the top. But the problem with that is you have the product of like n to the 5 halves. You have to be careful because look, it's so close, right? What are the terms on top that are really going to matter here, just in terms of doing some hand-waving analysis? This thing is going to matter, right? Because it's going to be n to the 5 halves, right? And this thing is going to matter. Yeah, you have to be really careful because it's square root. You can't really do it. You're going to end up with 5n to the what power? To the fourth. Oh, you just said 5n to the fourth. I see. So what do we think? What's our intuition say that this might actually go to? If you end up with 5, the thing on top looks like it's going to 5n to the fourth. The bottom is 5n to the fourth. So it probably looks like this limit is going to what? looks like it's going to 1. Is it good enough? Do we feel satiated enough? Not annoying, but it's something that you need to be aware of. You've done this before where you can take this right here and divide. Let me just write it out and let's see if you can see it. It's going to be the limit as n goes to infinity of 2n to the 5 halves plus 3n to the 3 halves, hold on, over 2 times the square root of 5 plus n to the 5th. What are we going to divide everything by? No, just the highest power, n to the 5 halves, exactly. The reason you do that is you end up with what you're dividing by 1, which does that change anything about the final answer? No. You end up with 2 plus 3 over what? 3 over n? Over, what do you end up with here? 2 square root what? 2 root what? 5 over n to the, not n squared, n to the 5th. 5 over n to the 5th plus what? N to the 5th over n to the 5th. It goes in when you translate it inside, you have to square it because it's going inside there, right? Why is that kind of nice? Well, what happens here? What does the top become? 0. This goes to 1, and this goes to, so end up with 2 over 2 times the square root of 1, which is 1. So there you go.